let us talk about ventilation. Ventilation. I like to begin my discussion on ventilation with a little question. Suppose you're told that a patient or a person at the time of admission had a respiratory rate of 15 per minute, described as being regular. Several hours later, the respiratory rate became 40 per minute, and it's described as being rapid, of course, and shallow. Can you tell me what pH changes would you expect in this patient? Would you expect this patient to become acidotic, or would you expect this patient to become alkalotic? I'll give you a moment to think about this. Notice the respiratory rate change from 15 per minute to 40 per minute, and it's described as being rapid and shallow. Now, if you have an answer, hold on to it, and we'll see if you're correct. Let's apply this. Let's understand the principles that this question is trying to teach. If this represents the lung, this, of course, is the pleura. We can say that the lung consists of two functional zones. What are these two functional zones? First, the conducting zone and the respiratory zone. The conducting zone, this consists of the airways, the bronchus, the bronchiole, trachea, all the way out the nostrils. This is the airways, the conducting zone. No exchange takes place here. No exchange of gases. The respiratory zone, on the other hand, this is where the alveoli are found. And this is where exchange takes place. Therefore, because of that, the conducting zone, the air that is trapped or in the conducting zone, is often referred to as dead space, physiological dead space. In a normal person, this measures to be approximately 150 mil. In fact, we say 1 mil per pound, expecting the normal person to weigh 150 pounds. So 1 mil per pound. So if you're weighing 200 pounds, one would expect your dead space to be about 200 mils. That's a sort of guesstimate. Now, so therefore, the volume of the conducting zone is approximately 150 mils. Now, in the question that I asked, this patient respiratory rate went from 15 per minute to 40 per minute. Rapid and shallow, key word. If he's breathing shallow, he's mostly exchanging air from the conducting zone. In other words, he has decreased or depressed his alveolar ventilation because of the rapid movement of air. He is not going deep enough. So therefore, what is the source of carbon dioxide? Of course, carbon dioxide comes from the blood into the alveoli. So to get rid of that carbon dioxide, you have to have alveolar ventilation. You have to have the respiratory zone involvement. This patient is mostly exchanging air from his conducting zone. Therefore, he is accumulating his carbon dioxide. Therefore, he will most likely become acidotic. Now let me pause. The principle here, we want you to differentiate between alveolar ventilation and hyperrespiration. They're not necessarily the same. Hyperrespiration and hyperventilation are not necessarily the same. Whenever we're having alveolar involvement, that is the true definition when we say the patient is hyperventilate. He is now blowing out his carbon dioxide. Shallow breathing, deep breathing are different. Can you breathe deep and fast at the same time? Try it. The faster you breathe, you're giving up depth to maintain rate. To breathe deep, you have to do what? Slow down and breathe deep. Now you are involving the alveoli. And this is the concept we want to bring for you to appreciate the difference between shallow respiration, which is conducting zone, and deep ventilation, which is alveolus. Now, having said that, let us talk about ventilation. We can say that ventilation, total ventilation, let's write that as VT, total ventilation, is a sum of conducting zone and respiratory zone. Ventilatory rate, we will now multiply that by the respiratory rate. Conducting zone plus respiratory zone, this is tidal volume. So therefore, total ventilation is tidal volume times respiratory rate. In a normal person, we expect tidal volume, we said, to be 500 mils. Respiratory rate to be 15 per minute. So therefore, in a normal person, we expect at least 7,500 mils per minute of air being in and out of the system. Now, question, does all of this air reaches the alveolus? Not really. Alveolar ventilation, therefore, will be tidal volume minus dead space, because we said the air that is trapped in the dead space is not physiologically functional. It's not being used. Times respiratory rate. What then is the alveolar ventilation in a normal person? 500 tidal volume, but dead space is 150 mils. Respiratory rate is then 15. So what do we have? This is equal to 350 times 15, of course, per minute. And this will give us, if you're doing the math quickly with me, 5,250 mils per minute. I want you to make note. The total amount of air that was brought into the system, 7,500 per minute. Normal lung. How much actually reached the alveoli? 5,000 approximately. Therefore, every minute, 2,000 mils are lost in the dead space. What does this tell us? It tells us that we have to be very conscious of dead space. Dead space can affect eventual alveolar ventilation. For example, if we are to increase dead space, what will happen to alveolar ventilation? It can very well decrease. We already have physiological dead space. We can also have diseases that can add to that, what we would call pathological dead space. Can you think of a disease that can possibly increase dead space? Give you a second to think about that. Did you say emphysema? Then that's correct. Emphysema. What's happening in emphysema? Bulbous alveoli trapping air. So therefore, that air that is trapped in the alveoli is not involved in exchange. It becomes part of dead space. So therefore, alveolar ventilation is inverse to dead space. If we increase dead space, we decrease alveolar ventilation. And if we decrease alveolar ventilation, what will that mean? It means we are not blowing our carbon dioxide out. This will now give me an increase in alveolar carbon dioxide. And this explains why an emphysematous patient will develop hypercapnic acidosis because of the increase in dead space. Now, this concept is important and we want you to pay attention to that. Now, the next thing we want to bring your attention to is comparing tidal volume and rate. What do we mean by that? Let's suppose the exam asks you, here is patient A. Let's say we have tidal volume, we have respiratory rate. Patient B. Tidal volume of patient A, let's say 400 mils. Respiratory rate 10 per minute. Patient B, let's say 200, and respiratory rate 20 per minute. And you're asked which one has the higher, would you expect of the two to have the higher PO2? Which one would you expect to have the higher PCO2? And which one would you expect to have the higher pH? Now, when you multiply tidal volume by respiratory rate, you've done that already, I'm sure, 400 by 10, 200 by 20, you've got the same answer. So the total ventilation is the same. So how do we distinguish and make a clinical estimate as to which one would you expect to have the higher PO2, the higher carbon dioxide, and the higher pH, and for that matter, the higher ventilation? Well, the best way to conceptualize that, let's develop a table, and you'll come back and answer that question all by yourself. Let us develop a table. Let's put rate on one side of a table and depth on one side of a table. We said that the more rate you have, the more conducting zone involvement you'll have. The faster you breathe, the shallower you get. The more depth, the more respiratory zone involvement you'll have. Now, the more conducting zone involvement, that means the more you are keeping or accumulating or retaining carbon dioxide, shallow breathing. The more depth, the more you're blowing out carbon dioxide, so your carbon dioxide goes down. The more depth you have, the more oxygen you will have because you are bringing in oxygen to the system. The more rate you have with the shallow breathing, you will have less oxygen into the system. Now, if you have an increase in carbon dioxide, this will give you a lower pH. And if you have a decrease in carbon dioxide, this will give you a higher pH. So therefore, we can develop a sort of mantra where we say, rate is to carbon dioxide as depth is to oxygen. That's a good guideline. Can you say that for me? Can you repeat it? Rate is to carbon dioxide as depth is to oxygen. Now that's all we need to know. Let me take you back to this question we have. Which one would you expect to have the higher? Notice we said we are comparing A and B. We are not necessarily saying higher in terms of higher than normal or lower than normal. But between A and B, which one would you expect to have the higher oxygen? Remember we said that rate is to what? Carbon dioxide. Who's got the higher rate? B. Depth is to what? Oxygen. Who's got the higher depth or the greater depth? Patient A. All that's what we need. So therefore, the higher oxygen will be the person or the patient with the greater depth, which will be patient A. Higher carbon dioxide, the one with the greater rate. And higher pH, of course, will be the one with the less carbon dioxide, higher oxygen, which is A. Isn't that simple enough? We can just look at it in an exam and we can conceptualize and come to an understanding of how rate and depth affect oxygen, carbon dioxide, and pH by extension. Now, having said that, ladies and gentlemen, we now want to bring our attention to composition of the air that we breathe in. Let's look at this diagram here. Composition of the air that we breathe in. Sometimes the exam asks a very simple question. And here is the question. A normal person during expiration, which of the following is least likely or not expected to be found in the conducting zone? Let me repeat that question. A normal person during expiration, which of the following would be least likely to be found in the conducting zone? Another question they ask, which is more appropriate, I would rather ask this. In a normal person, which of the following is not expected or least expected in the conducting zone during inspiration? During inspiration. We'll answer both questions. Now, during expiration, conducting zone, what would we expect to find there? We'll expect to find carbon dioxide in the conducting zone. The source of carbon dioxide, the blood, the alveolus. Will we expect to find oxygen in the conducting zone? Yes, because even though we inhale 21%, we do not dissolve all of that oxygen. Some of it is also blown out back again. So therefore, we will find oxygen, we will find carbon dioxide, we will find nitrogen, we will find all of these gases in the conducting zone during expiration. But the least, of course, will be carbon dioxide. Now, what about at the end of inspiration? Now, here's a tricky one. In a normal person breathing normal atmosphere, which of the following gases is not expected or least expected in the conducting zone at the end of inspiration? At the end of inspiration. Answer, and this is the catch. We do not expect carbon dioxide in the conducting zone in a person normal breathing normal atmosphere. This question may seem unfair. The idea is to differentiate between room air and atmosphere. In room air, you will find carbon dioxide. It's a pollutant. But in normal atmosphere, we are not going to find, or we do not expect to find, carbon dioxide. So whenever they ask this question, it's a little bit unfair. The idea is to get us to define and differentiate between room air, there is carbon dioxide, pollution, we added there, but normal atmosphere should have no carbon dioxide, minimum carbon dioxide, and that's why politically that's the big debate now. Leaving carbon footprints. We are talking about the level of carbon dioxide that is put into the air, pollution, ozone. You've been part of that discussion politically. Key point, just to make sure you remember, at the end of inspiration, we do not expect to find carbon dioxide in the conducting zone in someone breathing normal atmosphere. Now, having said that, ladies and gentlemen, we talked about dead space. We talked about alveolar dead space, physiological dead space. Dead space can be due to physiological dead space. Dead space can be due to pathological dead space, and we give an example of that. And the example we talked about there was emphysema, which is classical for that.